Check.
Hello.
Okay, we can maybe get started. It's a great pleasure to welcome Atish after many years to ICTS. And of course, today Atish will be giving the Salam lecture in the evening, to which I hope you'll all come. But we also decided to squeeze in his very tight schedule a seminar by him as well. So he'll tell us today about edge modes in de Sitter.
On stringy horizons.
On stringy horizons.
Okay, so it's really a pleasure to be back at ICTS. So after some years. So I will talk about some recent work with so this is in collaboration with a postdoc at ICTP and Upamanyu. Yeah. Should I use yellow? Should I use yellow? Is this better? Or should I write? No, I think. Okay, so let me just say a few words. If you have a Euclidean path integral on some manifold cross S1, so you have some Euclidean path integral. On M cross S1. Then we know that following Feynman's standard steps, this admits a natural interpretation as a trace. Where beta is the length of the S1. H is the translations. And the Hilbert space is like wave functions which are defined on M, like L2 norm states on M. So this is a very standard thing that you're used to seeing. But if I give you some generic manifold, so for example, you can take M to be S2 cross S1. Sorry, I mean, M can be S2 and then you have your wave functions are living on S2 and your time is translating around S1. But if you have, for a generic Euclidean manifold, there is no such interpretation. So for example, if you take on S3, let's say, then there is no natural notion of time slicing that you can do, by which you can give a state counting interpretation of this kind. But in a series of papers And notice that this is really like the Euclidean DS3. So in general, you can have Euclidean DS D plus 1 will be just a sphere. But it turns out that actually, so let's call this partition function. Suppose I have some field I. Let me call this partition function. This is I put a hat because it's the spacetime partition function, z hat of I. And what was shown by these people, Aninos, Denef, Law, and Sun, in a very nice paper, that this has a nearly thermal interpretation. So they showed that log Zi, and I can, so I is a field with arbitrary mass and arbitrary spin. It can be some complicated representation and a complicated, and they had a general formula for any such path integral of any field. Free field, yeah. One loop free field. That it nearly has this kind of an interpretation, where this has a thermal interpretation, but there is a small missing piece which seems to live on a codimension 2 surface, which they call the edge modes. And this has also some antecedents in ADS-CF3 and higher spin theories and so on, where Klebanov, various people had run into this. So this is how the technology was developed. Exactly. So that's the motivation. My motivation is ultimately to understand the physics near the Rindler horizon, because it is related to entanglement. Most of the interesting stuff is in the second.
First term, when you say has a thermal interpretation, but what? Is it some foliation?
So I will come to that. So basically, if you look at Euclidean de Sitter and analytically, so the point is that given a Euclidean calculation, what is the Lorentzian interpretation? And Lorentzian de Sitter is like this, and there is a static patch. And it would be, and we know that an observer moving in a static patch is basically like an accelerated observer. So in fact, near the de Sitter horizon is very much like an observer near a black hole horizon. So the physics of the horizon is very similar. And unlike in the case of a black hole, de Sitter has a lot of symmetry. So some very explicit formulas are possible, which is why we went down this track, even though or even compared to Rindler-Minkowski horizon, Rindler is not really amenable to, because if you go to Rindler coordinates, the theory is basically non-Gaussian, because you have terms, even the free theory doesn't look free in the Rindler coordinates. So,
you need a isometry around the S1 for S1 translation.
So in general, no, what I'm saying is that for a generic manifold, there is no such interpretation possible. Only for Euclidean de Sitter D plus 1 and Euclidean anti-de Sitter D plus 1, they found such a solution, interpretation, basically because group theory is quite powerful and you can calculate things. Otherwise, you have to do some quasi-normal mode analysis and so on. It's not something that is easily doable.
One might expect that if there's an isometry, then
yeah.
wherever the subtle strings, there will be some edge.
Correct. Exactly. That's the basically the. So what is the physical reason for this? So let's call this Hamiltonian H Rindler or H static patch. And basically the interpretation of this is that Zi bulk is a trace over e to the minus beta H static patch, where beta is 2 pi, as we know in appropriate units. And the fact that the origin is exactly what Ashok was saying, that there is a fixed point in the Euclidean continuation. This is just a rotation, Hamiltonian, and there is a fixed point. And the fixed point corresponds to what is known as the bifurcate horizon in the black hole. So, and as we know, all the interesting physics of black holes, from Hawking radiation and everything, entropy, etc., really has to do with this point on the space-time diagram, because of particles going around and not, things like that. Thermal bath, all this really follows because of the special properties of this bifurcate horizon, which is a fixed point here. And because so the main point is that, unlike here, where there is a nice slicing for everywhere, the slicing kind of breaks down. The space slicing becomes singular near the horizon. And that's the reason why you have some edge modes. Now, what is nice is that you would have been forced to put some kind of brick wall condition to deal with this. I mean, you wouldn't know how to do it. If you try to do it ad hoc way, people have tried it, and you get quite ugly formulas, and it's really not manageable. But here, you find that you can actually write down very nice explicit answers. Because this side you can calculate very easily. This is just a partition function on S3. So for any spin or Sn, and this you can do just by simple harmonic analysis or YLMs for the spheres. So this you know, and you see that there is a mismatch. And the
Gravitational constraints don't play any role in this.
No, because it's one loop. It's one loop. There's no gravity. So it's to be really to be interpreted as the entanglement, contribution to entanglement entropy. I mean, that is my interest also. Yes. Not generic M. Let's call this N. For a generic N, because there is no time-like slicing you can think of, right? There is no natural time-like slicing. Of course, you can do some arbitrary time-like slicing, and you can try to, but there is no natural, straightforward interpretation like this. No, in this case, because de Sitter is so symmetric, you basically calculate this, and you see that this is left over. And on S3, let's be concrete. So in 3 dimensions, de Sitter 3 Euclideanized is just S3. So S3 is a very simple manifold. We just need to, the Laplacian are just given, can be solved. For a scalar Laplacian, you'll just get the analogs of YLMs as the. There is a difference, particularly important in anti-de Sitter.
Yeah. So
That's why we focused on de Sitter horizons. Although there is a very similar story in anti-de Sitter, but you have to treat even and odd separately. But tell me, what is your reason for thinking about it like that?
Yeah, whether this sort of decomposition in terms of a bulk and an edge mode holds also, say, for de Sitter 4 or.
No, for de Sitter there is no.
So even an odd.
Even an odd, but for anti-de Sitter there is a distinction.
Yeah, that's why I was asking.
So in anti-de Sitter, Zimos analyzed it nicely. And you have to also regularize the infinite volume, and there are issues like that. So
For anti-de Sitter, digital, the circle doesn't contract, right? You have a global time.
But it's really Rindler anti-de Sitter. Rindler. So the point is that the story, since the physics is very, Zemo gave an interpretation in terms of Rindler anti-de Sitter. Huh? Yes, it's only for the static patch using this particular Hamiltonian. But the nice kind of a magic is that you can write both of these quantities in terms of some characters of the de Sitter group. So it's like group theoretic. So these are called actually Harish-Chandra characters. I mean, we have a Harish-Chandra room here. Huh? Wing, Harish-Chandra. Okay, so I mean, you know the notion of a character, right? You just take trace of e to the minus mu, some generator of the group, and that's a character of that group. Now, when you are dealing with infinite dimensional representations, which is the case with non-compact groups like de Sitter, there are some subtleties. So for finite dimensional thing, the trace is well defined, this is well defined. So this is what Harish-Chandra's famous work is about, really defining infinite dimensional representations of non-compact groups. And there is a very nice story. All this can be written exactly in terms of characters. So I'll just describe it very quickly. So let me just say, I will describe edge modes in quantum field theory. And to be concrete, all these results can be generalized to higher de Sitter, but just to be concrete, I'll be in de Sitter 3. So in de Sitter 3, so it's really signature 1, 2, right? So you can think of de Sitter 3 as some kind of an infrared regulator of Lorentzian space, right? Normal Minkowski space. I mean, in the limit of r going to infinity, or let's call the length, there's a length scale, curvature length scale, going to infinity, this will go to R1, 2. And here, all states are represented by representations of the Poincare group, which is the inhomogeneous Lorentz group, ISO 1, 2. And here, they will be SO1, 3, which is the symmetry group of SO3, which, if you remember, there is this Wigner-Inonu contraction. Something, there are dots somewhere. But you're sort of used to the representation theory a la Wigner, that all states are labeled by masses and spins, right? The infinite dimensional representation of ISO 1, 2, for example, is just labeled by P mu. But there is a quadratic Casimir, P square is equal to M square. And then you go to the little group, you go to the rest frame of that particle. It's a massive representation. The little group is whatever it is. In this case, it will be SO2. And you look at the representation of that, and that gives you the spin of the particle. So it is represented, this is an infinite dimensional representation, not finite dimensional. It is unitary. And it is labeled by 2 quadratic Casimirs, or 2 Casimir. Likewise, here, the representation is labeled by nu and s, with a relation that nu square is equal to L square M square minus S minus 1 square. So what we are doing, we are considering a field phi with spin S and mass M. Now what I mean here actually is that I'm actually going to take a tensor symmetric tensor with indices mu1 to mu(s) and mass m. Okay? And if you use some kind of, I will come to that in the end, you can interpret this in terms of, so as you know, given a path integral, you can interpret it, I mean, given a quantum field and you construct its Fock space, the Fock space automatically furnishes an irreducible representation of the Poincare group and vice versa, right? So there is this, I mean, this you learn in your QFT course, fields and states are in one-to-one correspondence. You can have a not to one-to-one correspondence, maybe you can have different helicities, all described by a field, but basically, instead of thinking of the electron field, Dirac field, you could start with just the representations with spin half, representations of Poincare group, put them together in an appropriate way, and that will come out, when you quantize the Dirac field, that will come out as the Fock space of the Dirac field, right? So this is the normal procedure that we do. So, you know, sometimes we are so used to this that we forget this. It's actually quite a non-trivial set of steps. And from here, we go to Euclidean. Where the group theory is actually quite different, you know, because here you'll be dealing with group theory will be SO4 representation theory, which is a compact group. It does not have any infinite dimensional unitary representations. So the path integral computed in Euclidean theory can be interpreted as a field path integral by some analytic continuation. And then in turn, that has an interpretation in terms of states, and which is what we are looking for, the Lorentzian interpretation in terms of states. So I just want to write down some formulas, but it should be kind of reasonably clear. So if you take such a field and if you calculate log z, then you know that basically you're going to get a log of a determinant, right? So you're going to get a log of the determinant. But that we know we can write it as a trace log. And the log can be represented using Schwinger representation as some kind of an integral dt over 2t e to the minus t box plus m square, right? Roughly. Some factors of half, actually. Maybe there is a factor of half here. And it is usually divergent. So it's going from, if it goes from 0 to infinity, it will be divergent. So normally you put a proper time cutoff, and that's the whole point, that in quantum field theory, this answer is divergent. Okay, but as we know, string theory has some magical properties because of which it is not divergent in string theory, because the limits are automatically fixed with the string length. But this, you can write down actually pretty much by inspection. I think Rajesh and company also wrote a paper on this, together with Justin and Gabardiel. So it looks like this. Basically, you have a Laplacian. So you need to know the eigenvalues of the Laplacian and the multiplicities, right? So imagine that you are doing the calculation on S2. And the eigenvalues of Laplacian is just LL plus 1. And the multiplicity is 2L plus 1, right? So you just have to calculate 2L plus 1 e to the minus L square t and sum over L. And that will give you the answer. The story is a bit more complicated, but not very much more complicated. And yeah, sorry, sir, trace. Yeah, and this is a trace. The capital trace refers to space-time trace in a space-time. We will shortly go to a worldsheet trace. That's what our goal is, where I will denote it by small trace. So D4NS, sum over n going from -1. So this is some calculation that people have done. It's actually also an interesting and non-trivial calculation to go through. But this is roughly the analog of LL plus 1. And this is the analog of 2L plus 1. And by some manipulation, now you want to interpret this in terms of, so how will you go about it, right? You will sort of say that if I have a frequency omega, right, a thermal partition function you can write down, right? Thermal partition function for a mode of frequency omega is just log, it's just the Einstein, Bose-Einstein, e to the minus beta omega divided by 1 minus e to the minus beta omega, right? And the omega is, of course, all the frequencies, you have to sum over them. So to get to the, so this is a partition function, this is a trace, and you want to take the logarithm of that. So you're going to get some logarithm of log of e to the minus beta omega, and you can do some manipulations, which I will not go into. But after some manipulation, you can write it as, I mean, it's a fairly straightforward, so I'm writing it from 0 to infinity, but it's always understood to be going from with some appropriate cutoff.
The same thing manipulated into this.
Yeah, no. So yeah, this is the same thing manipulated into this. And this you can interpret very easily along these lines. You can show that that is equal to the logarithm of a partition function of just summing over various modes.
So it's thermal gas.
It's thermal gas interpretation. So this has the thermal gas interpretation. So basically, this is a completely explicit formula. You can manipulate this to write it like this. And this you can interpret as thermal, and what remains is edge. You can show that when spin is non-zero, there is always an edge mode. So for a scalar field, you don't notice it, that there are edge modes. So we will basically be dealing with the principal series. There are, it turns out that only the, if you're looking at massive representations, which is what we will do, basically you can deal with only with the principal series. So no, I'm going to write down what is chi, and that's only for the principal series, but there are similar formulas for the complementary series. So there are some very explicit formulas. I nu plus e to the minus u 1 minus I nu 1 minus e to the minus u whole square.
Yeah, that's good. And we had just a normal quantum field, say in class, right? Here we could start from the path integral, and we have formal manipulation to express this as a thermal gas partition, right?
Yeah.
Can something similar be done here? I mean, instead of doing this explicit calculation, if you just start with the integral path integral.
In flat space.
Or even this itself, okay? And just manipulate it to bring it into this form.
Yeah. But that's basically what it, I mean, the steps to go from here to there are pretty one-page calculation. It's not something.
Yeah, but you are using the explicit form of the partition function, right? I'm just saying that just formally manipulate the path integral itself without worrying about what
To show that it will always have this form.
Yeah. Because normally in quantum field theory, when you do it, right, you can do a formal manipulation.
You should be able, you're saying that along these lines. Yeah.
So you don't explicitly do it every time, right?
Correct. I mean,
the extra thing is there will be this edge mode, right?
No, but also like when you do the formal thing, you will be left with a formal Hamiltonian, and you wouldn't know what that actual trace is.
Like in the usual, you do a Legendre transform. That's how you would get the Hamiltonian. Here also, presumably, you do the similar kind. You're kind of, normally you go from the Hamiltonian to the Lagrangian by setting all these complete set of states. I think maybe what Ashok is saying is to reverse that
Yeah.
logic.
Yeah.
And
Yeah, I think, I mean,
Somehow that complete set of states will not be complete unless you add this H. Right?
You're saying that like basically because your Hilbert space is has this kind of slicing has a problem at the fixed point, and that should show up in the. Yeah, I think that it should be possible, and I think it's kind of. I mean, yeah, the steps here are fairly straightforward. So maybe if you just dig into it, it might be almost implicit there.
so it's just to understand, you started with the Euclidean path integral.
Yes.
On S3.
Yes.
And then when you went to from the middle step to the last step, then you did this analytic continuation and wrote it in terms of the discrete series.
No. We didn't do analytic continuation, right? I mean, we just wrote it. Like here, we don't do analytic continuation. We just write it.
Just the Euclidean DC.
I mean, it's really trace e to the minus beta h.
Right.
But yeah, but here it will be SO1, 3 representation. Like there, the Hamiltonian is acting on a Hilbert space. Yeah, so there is a hidden Hilbert space which you uncover like you do there, like you do in a normal way.
Because the first one gives you in terms of SO4.
Right? Correct. And what is going to appear here are exactly what you said. It's the principal series of SO1, 3 and not of SO4. So the Hilbert space appears, right, as we do the calculus. Like in the case of, so let me maybe give you.
I mean, you will see really the SO2 part.
In this case, you will see, but SO2, but also P square is a kind of, is already taken care of. Yes, yeah, exactly. But I mean, you can put it all together. So I think to keep it in mind, if you just take flat space, yeah, maybe it's a good idea. Right? In flat space, it would be like dt upon t e to the minus t p square plus m square. Right? That's your path integral. Suppose you were doing it on R3. And that you will interpret as, of course, SO1, 2. Of course, here you'll have to invent the Rindler temperature. If you just interpret it with the usual slicing, you will not get this thermal interpretation. But suppose you were doing it at finite temperature, a gas at finite temperature. If you were doing something more like that, then you will get a gas at finite temperature with sum over this Matsubara frequencies kind of thing. And you will rewrite it and you will discover that it's Poisson estimation and so on. Okay, but I just want to write down explicit formulas that are there. So DSD are SOD spin degeneracies. So this is where the representation theory sort of, this is a little group. I'm doing, in my notation, DS3 is really, I'm doing DSD plus 1. So DS3 corresponds to D is equal to 2. And the edge modes, surprisingly, and this is a story that works in all dimensions, are just same character of not SO1, 3, but SO1, 1. I mean, de Sitter group 2. In this case, it will be SO1, 1. I mean, it's a co-dimension 2 surface. So in the case of de Sitter, yeah, if you were in 4 dimensions, if you're doing de Sitter 4, it would be SO1, 5 and SO1, 2. Like that. In general, you will go from SO1, D plus 1 to SO1, D minus 1. Basically, the bifurcation surface is co-dimension 2. So you drop 2 dimensions, not 1 dimension. Yeah. So I'm going to give you that in a moment. This is it turns out that, but I just want to tell you that There is a lot of technology that has gone into this, which you can read. It's a very nice paper. I recommend Aninos Denef. It's a 100-page paper, so it's like, it has everything in a way. Law and Sun. But you can see that this fact that it is dropping 2 dimensions is reflected by, in general, this will be SO D plus whatever, D, and here it will be SO D minus 2. Yeah, here it is 4. You might be, but that's how it comes out. It comes out from a particular identity that D4NS is equal to, there is some identity which is behind this. This is an identity about just symmetric tensors of SO whatever. So you have n columns and dimension, etc., etc. S, so symmetric S tensor and so on, and there is a identity. I mean, this is just a completely, what is it called? Counting kind of combinatoric identity. Okay. So what is nice is that these are very well-defined Harish-Chandra characters of the digital group. If you try to do it in an ad hoc way, actually you'll land up in a lot of trouble. And this is what this paper explains. That you either get divergences, you don't get proper answers. But if you just follow group theory nicely, you get very nice answers. So in our particular case, this is just simply equal to 2n plus 1 whole square.
The actual answer is divergent and that divergence.
No, not this divergent, but there is also divergence when you compute the trace. So the point is that because it's an infinite dimensional representation, the Harish-Chandra characters are well defined, whereas some naive traces are not well defined.
You put U equal to 0, the identity is
Exactly. That's another way to say that.
But it could somehow just a different choice of basically the same divergence getting transferred to that one or not?
No, actually. So the thing is that if
that is a UV divergence.
I think this is an IR.
No, I mean, the question is that whether, no, so you have, chi is defined to be e to the minus 2 pi H static. This is just the generator of boosts. If you think of an SO 1, 4, it's like a 1, 1, 3 boost, let's say. And that is a non-compact generator. And if you compute the trace, if you don't define it properly, you will get divergences. Those divergences are independent of the...
That's for fixed. Eigenvalue there will be infinite number of states. That term.
No, because the fact is that this is a trace over some Hilbert space, which is an infinite dimensional unitary representation.
Yeah.
And that trace may not be defined unless you do things properly.
I think it's like a volume.
So for a fixed Hs, then there will be infinite number of states.
For
that
fixed?
That will be
For fixed what?
The Hs eigenvalue. If the infinite number of states, then it is something. Right?
No, I think these are well defined. It is just, I think that if you take character of an arbitrary group element, it may.
No, I mean, the question is that how do you define the character of a group element for a non-compact group? I mean, you have to be careful about that. And basically, Harish-Chandra tells you how to be careful about it.
I'm just asking the naive divergence is coming from the high eigenvalue or low eigenvalue? The sum is divergent, right? But is it from the high eigenvalue or low eigenvalue?
No, the sum is finite. I think like these characters are all finite. It's only for some, if I take, say, the identity element, that is like...
See, it's a little bit like, suppose you were computing, suppose you're computing trace t square for a harmonic oscillator, okay, not for a free particle. This trace is divergent if you treat it, you might be tempted to say that, okay, I diagonalize this operator. And then what will you get? You will get P e to the minus TP squared E dP. And because of this norm is not, these are non-normalizable states, you will get a divergence, which is basically the volume divergence.
Integral dp certainly is not the correct.
So doing it in this manner, in this basis is not the correct thing. So you have to define it, maybe you would define it going to the, maybe the harmonic oscillator basis, where the P square is defined in terms of A and A dagger, and you evaluate the trace there. So I think it's basically that kind of an analysis which has to be done. Yeah, so I think it's not because it is not trace class, but it's how do you, in which basis you perform the trace? I mean, you have to perform the trace properly.
Yes.
Yeah, there is also, basically it's a trying to make sure the sense of an infinite, like. Harish-Chandra's regulator in some sense. Yeah, I mean, how did he regulate it? No, in this particular case, it actually comes out quite a straightforward way. You don't even need a regulator. If you go to some certain basis, you just get a it's a good basis, but there may be some way to connect it to our normal intuition about how you would have done it. Okay, so this is, okay, I want to, now I have only 15 minutes, right? Okay, so I want, till you're hungry. So now I want to do, so it's a very nice story and we have explicit formulas for any spin. Now I want to do, yeah? Suppose you want to solve the eigenvalue problem. The Lorentzian calculus. Yeah. Then it's a very tricky problem. It's a very tricky problem if you try to put some kind of a brick wall and so on, and then you will get into all kinds of difficulties if you try to do it like that. There may be ways in which maybe we can talk later. Yeah. So people have tried this brick wall regularization. It doesn't work, yeah. So this somehow, following this route gives you some very nice, group theory sort of dictates a very nice regularization. And for which you have nice formulas already done by somebody, because it's sort of group theory and somebody has done the calculation for you. So now the question is, I just want to remind, I'm going behind the horizon, okay. So this is the horizon, no? Here is the horizon, right? Okay. So edge modes in string theory. Now, given a de Sitter 3 answer for all fields, I can imagine doing bosonic string theory. Let's say S1 to the power 23. Right? I just compactify to so many dimensions, to 3 dimensions. And then I replace this factor. I regard this as just a regulator by ds1, 2, with L as an IR regulator. And one can do it also in ADS, where things are a bit better, but it has some other problems. So we decided to do first in de Sitter, but we will also discuss later in anti-de Sitter. And let me remind you, a very nice calculation was just done by Polchinski. But suppose you calculate, so the idea is that, can you go from string field theory I mean, don't be scared. I think it's not the kind of string filter that Ashok does. Here, this is a free string field theory. So it's just a collection of many fields which correspond to string theory, right? So in string theory, you just have several fields with some mi square si. And if you're in R1, comma 2, then they're just labeled by helicities. So the group theory is actually simple. If you go to higher dimensions, then the group theory becomes more complicated. So helicity and that labeling S is basically related to each other. That labeling S, you have to include both positive and negative helicity. But other than that, it's all abelian. The little group is SO2, which is abelian. And the only state where the complementary series is, okay, so the point is that you have some states labeled by ISO1, comma 2, which you're going to interpret in terms of SO1, comma 3 representation. And you expect that there should be one-to-one map because we live in a de Sitter space with extremely low curvature, and you cannot tell the difference between Minkowski spacetime and de Sitter spacetime. So there has to be some this is the Wigner contraction idea. And they're labeled by mi square and si. And so you can just define the log of the string field partition function is the sum over all modes. And this you interpret as a without the hat, which is the worldsheet partition function. Okay, and this is something that you know. It comes from the fact that in string theory worldsheet, you're sort of summing over a loop. Whereas in a space-time calculation, you're doing some exponential of the loop diagrams. Right? Because if you do the space-time diagram, you'll get one loop. I mean, you'll get this kind of several loops, even in a free theory. And that is, if you take the logarithm, you'll just get this is a well-known notion that the logarithm of the space-time partition function at one loop is the worldsheet partition function.
It's a beta-dependent part that comes out currently. The load-dependent part has some desire.
There you have to set it by hand. There you have to restrict the domain. Yeah, field theory will have that divergence. So the cosmological constant will have that divergence, which you have to set by hand.
Then you exactly get that.
Yeah, exactly. So the question is, but even for the divergent part, the fact is that you get a modular invariant answer, and then you're allowed to, do that. So the question is, can we get a modular invariant answer, and can we restrict to a domain?
Invariant by itself. That's
why
why
what he's saying is that if you just look at the integral, you can think of the integral over the infinite number of copies of the because you get the whole thing.
correct.
And then by hand, you'll say by hand.
You'll have to send it by hand.
Yeah.
But you'll see that for the edge modes, what happens is a bit like the beta dependent part. Okay, but
Dependent, then there's no confusion.
there is no confusion. So you should get a modular invariant answer. I mean, you have to do some work. But there again, you interpret, you have to have this time-like winding modes. So there is a reinterpretation that is required, okay? And it's not obvious. Here it happens in somewhat non-trivial way, and I will explain that. No, you will not have winding mode. So you get something else.
The startle strings, then you don't have the one.
So now, if you just look at this answer, this is Euclidean answer. If you look at this, this is actually the bulk. You can actually identify this to that and this to that. And if you trace back the Euclidean calculation to Lorentzian calculation, it turns out this is really the edge and this is the bulk. Okay? So what you're supposed to do is you sum over, in the first case, you're going to sum over n plus 1 whole square e to the minus t mi squared, sum over I, right? And in the second case, you're going to do sum over s square e to the minus t mi square, si square sum over I. So this is your bulk. So when I drop the hat, I'm talking about the worldsheet partition function. Okay? And this should give you the one loop cosmological constant of bosonic string theory, properly renormalized, properly regularized in the infrared by the volume of de Sitter. And this you can very easily check. So basically, you know that you use the on-shell condition, mass shell condition, that mi square is equal to whatever, n plus n plus n bar, whatever, minus 2, whatever, with the constraint that n is equal to n bar, where n and n bar right moving oscillators. So it's basically like all the modes of the string an dagger an, right? Or alpha n dagger alpha n, and going from. And this you can do, and because of this n plus 1 factor, you can actually divide it by L square, and you take the large L limit. This is like a momentum integral. This becomes a dp p square, which is what you expect in 3 dimensions, with an L cube coming out. So this piece you can show following the steps of Kolchinsky and performing the sum over all states. This basically gives you L cube r to the 23. So if my circles have radius r, all of them, I will get r to the 23. You implement this constraint by introducing this additional Schwinger parameter, d tau 1, e to the minus 2 pi I, tau 1, sorry, n minus n tilde, let's say. And this basically becomes a worldsheet trace, starts to look like a worldsheet trace. Small trace, q to the L naught, or q to the n, q bar to the n tilde, minus 1. And when you sum over the bosonic string modes, you're guaranteed more or less. But it works out nicely, not surprisingly, but you will get something like L cube r to the 23 d to tau 2 square times lambda tau, which is the cosmological constant density of flat space. And lambda tau, if you remember, because you have 24 light cone oscillations of the string in the 20s, you will get this tau 2 to the 12 factor, and you will get eta tau, eta to the 24 square. No. What we're doing is that since we don't know how to do the worldsheet calculation near this horizon, we're going to follow the approach that Polchinski followed to get the worldsheet answer from spacetime. That we are going to imagine that a string loop, a worldsheet loop, yeah, the basic idea is this. This loop is sum over loops of various modes, right? A string contains all the particle modes of the string field. So there is one loop going for, let's say, the graviton, another one for phi, and if you sum over all of them, you should be able to reproduce the worldsheet diagram. That is the idea. And the test of whether you're doing it correctly or not is whether if you get a nice modular invariant answer or you don't succeed. So here, of course, you had to succeed because this is basically some way of regularization of the, that part is obvious. The question is that can we now apply the same method to the second term? And there you have to basically do, it's too noisy. So now you have, instead of this trace, you will have to do some kind of a trace over s plus s tilde whole square q to the n minus 1, q bar to the n tilde minus 1. Right? Because you have to evaluate all the. Now you notice that you're already down by 2 powers of n plus 1. So your final answer is going to be down codimension wise. It's going to be, it's like doing an integral dp rather than p square dp. So you're going to be down by 2 powers of. So I think it's already codimension. It's stuck at the horizon. But the question is that can we do this trace and can we do it in some reasonable way? And this basically you can, and what?
That age calculation.
Yeah.
Now you are putting that result using the string theory.
Yeah, so I'm going to use the string theory spectrum and put an index I, and I'm going to sum over all of them. It turns out, I mean, it's a relatively straightforward trace to evaluate. You can actually evaluate, and you can write everything in terms of you can sort of go to the grand canonical ensemble and write a z, which is e to the minus mu s plus s tilde. And you take 2 derivatives, that's always the easy thing to do. And when you do that, you end up getting this answer. You get L now, 2 powers less, I mean, divided by L to the string scale. The same lambda tau times tau 2 e2 tau plus tau 2 e2 tau bar. Where e2 tau so right now this is over a strip because you are doing a field theory calculation. So you don't know a priori.
The invariance I thought comes out after you do the.
But I mean, what I'm saying is that if you just did the field theory calculation, as in the Polchinski's case, there is no guarantee that you will get a modular answer.
It's the invariant thing after you do that.
Yeah, so we have to see whether we get a modular answer.
But
Is not modular invariant, yes, exactly.
That this ADS3 or DS3 is not a solution. It's not, it doesn't give us CF.
Yeah. So there is a constant term which we had to ignore. And we believe that it has to do with the, I mean, the answer actually. Correct. So there is a, we can do this in ADS3 and make it conformal invariant. We can do it on ADS3 cross S3, which is something that we're doing. So here there is a constant term that we have to drop, which we are not sure of. But I think it basically comes from some kind of central chart, like a space-time action not being a tadpole there. But let's look at this action, this expression. Now, the thing is that this domain can be mapped to the fundamental domain by modular transformation which belong to gamma infinity by gamma. So if gamma is SL to Z, and gamma infinity is the group of translations which leave the infinity fixed, which are basically generated by translations like that. Maybe plus or minus 1, I forget. But basically this is like the T part of the, so you know that SL to Z is generated by S, which takes tau to going to minus 1 upon tau, and T takes tau to tau plus 1. Repeated action of this generates gamma infinity. And if you mod it out, you get this coset. And they are labeled by C and D. Basically, if you start with ABCD, AD minus BC equal to 1, which is the SL to Z element, and then you remove one of, so you basically have 3 integers. Using the gamma infinity, which has 1 more integer, you're left with 2 integers to label each member of this coset. and you can label them by CD. So when you do that, tau 2 becomes, you can write this as over a fundamental domain. I will just write this part, sum over tau 2 to the power C tau plus D square, E2 hat tau, sorry. So E2, I forgot to tell you, E2 is the quasi-modular Eisenstein series, which has a completely explicit expression. So E2 is equal to 1 upon 2 pi I d by d tau of log of eta tau to the 24. It has a very nice 1 minus 24 sum. I mean, basically you take the eta function and you take its product form, take its logarithm and take the derivative. You're going to get a very nice Q expansion. It has a very nice Q expansion, but it is not modular. It is almost modular, so it's called a quasi-modular form. And you can very nicely complete it in terms of a modular form, which is, however, not holomorphic. It's a little bit, it's a baby version of mock modular forms. So because of this tau 2, it's a function not only just of tau, but tau and tau bar. But once you add this, it transforms like a weight 2 modular form. So basically, E2 tau goes as C tau plus D to the power square E2 hat tau. E2 hat tau goes to, when you take tau to A tau plus B, C tau plus D, right? So under tau going to A tau plus B, C tau plus D, E2 hat goes to C tau plus D whole square, E2 hat. So using that property, so basically, there is that constant piece that I'm explaining, that if you replace this tau 2 by E2 bar, you are left with a constant piece, which
By itself is not more.
yeah.
Lambda tau.
Lambda tau is our original this expression.
On a modular transform, minus 3 or
Yeah. So therefore it looks like, and you can actually show, it looks like that you're getting an expression which is lambda tau times some function of tau times E2 tau hat tau plus complex conjugate. And this is almost modular invariant. It looks like f of tau is actually tau 2 to the sum over tau 2 divided by C tau plus D whole square. Sorry. Tau 2 times C tau plus D whole square divided by C tau plus D whole square. So this C tau plus D comes because of the fact that when you do the modular transformation, because this is a modular form, it will give you a factor of C tau plus D whole square. And tau 2 itself also transforms in this manner. So the total function is of this form. And it seems to have the right properties to cancel the modular properties of this and to give you a modular expression. But this is not convergent. This sum is not convergent.
in one case you get C tau plus D square, in the you're going to have mod C tau plus D square, right?
Yeah, and you get mod C tau plus D whole square.
So that is there.
Yeah, there's a phase left over, and so it transforms in a 1,1 way, yeah, in a mixed way. It's a mixed transformation.
And the other one will have opposite.
And you have the opposite. So if this was a convergent expression, you're done, and you're expressed everything in terms of a modular expression on a keyhole.
Transform difference, yeah.
No, this is not modular. It has the modular transformation properties that cancel the modular transformation properties of E2 tau times tau.
So you cannot cancel for both E2 and each bar, right?
No. In that case, you'll get F tau bar.
Oh. But in the lambda, I want that.
Yeah.
So that's how I'm confused.
Correct. No, but when E2 hat transforms, it will give you C tau bar plus D whole square. Yeah. That's how this will change. Okay, let's follow.
You had tau 2 E2 hat and tau 3 E2 hat bar, right?
Yeah.
These two terms become opposite phase.
Opposite phase, exactly right. And but this transforms also in the opposite way compared to this. Because it has
That's different, right?
yeah, that's the difference.
Tau 2 always gives the same transform.
Yeah. So basically,
Mod,
yeah.
So in one term, you are getting C tau plus D square over mod C tau plus D square.
Yeah.
In the other term, you are getting
C tau bar plus D square. Yeah.
So it's not individually modular. Sum is not modular, right?
No. Then you have to multiply this by E2 tau. Okay.
E2 hat will transform and
E2 bar will transform in opposite way.
Yeah. But in this expression, so this was the expression, right?
no, the one below.
Then we go.
That is the one in the keyboard.
Yes.
Okay. So top one is
This is on the
so that's where this is. You are converting this to the keyhole.
yeah, converting it to the keyhole region. So let me we can come back to your. I mean, maybe I'll just let me finish the punch line.
If you are transferring it to keyhole region by using definite, right?
No, you can actually track down. You see, this has modular transformation property 2, 0, and this has modular transformation property 0, 2. So what you need is an object which transforms as -2, 0 here, an object which transforms as -0, -2. And that's what we will do now.
You will do by pi.
So let's first look at the first term, because the second term is a complex conjugate. It will work out the same way. So it turns out, so let's define this function f of tau. Sum over CD. So this will transform as 0, -2 that we want, or -2, 0. It has the right transformation properties. But the point is that it's not convergent. So we need to regularize it. And we can regularize it by defining a function f tau of s, where you put let me call it, you basically, f tau of s is defined as you put s here, and you put, you basically write tau 2 to the s and c tau plus d absolute value to the power 2s. Okay, so you just multiply this. This might look ad hoc, but it's basically like dimensional regularization, because if you change the number of dimensions in which you are doing the momentum integral, the Schwinger parameter will change, the number of Schwinger parameters will change. So taking s, so we want to take the limit s going to 0 in the end. If you do that, you can show that this is actually what is known as a mass lowering operator. It's like a lowering operator of a function f of s. And this is a non-holomorphic Eisenstein series. Which is modular invariant. And this derivative lowers its dimension to -2. You can check that the dimension of this operator is -2. And when you do the complex conjugation, you will get the complex conjugation. No, there is no divergence from 1 over s. The divergence is... Yeah, it's basically coming from s going to 0 limit. But that's the question. Eta 0 also has a S, so I will discuss that. So the point is that eta of S is actually very well studied function and very important function in number theory. And there is some story there which I don't want to go. But basically, instead of looking at, you can relate eta of S. There are some functions. It's like the Riemann zeta function has some symmetry properties that S going to 1 minus S. You can relate this and get rid of that 1 upon S factor to tau 1 minus S. So we want to study the behavior of this function at S goes to 0. But you could just as well, so you can, 1 upon S e to the tau S can be related by using some functional identities like the Riemann zeta function to the same function without the 1 upon S at 1 minus S, but S going as 1 minus. So just you're studying the asymptotics. I mean, you can do it directly here also, but this is easier because this has been studied in the literature. And this is a famous classic Kronecker limit formula, it's called. I mean, we were surprised to find this. We didn't know. I mean, so we were quite puzzled now what to do with this. But actually, it turns out in 1863, Kronecker had studied this limit. And this is actually some very well-studied formula. You can find it also in the Lang's textbook. So it's really a textbook result by now. That this goes as pi S minus 1 minus pi log tau 2 plus order S minus 1. The important point is that the coefficient of S1 upon S minus 1, where there is a pole, is actually independent of tau. So when this derivative operator acts on it, it doesn't give you anything. So after the regularization, if you take S going to 1 limit, it's a bit like the adding n, this famous Ramanujan's formula, which gives you minus 1 upon 12. When you regularize it and you take the derivative, this term just drops out, and you take the mass lowering operator acting on this. And what you end up getting is E2 bar hat. The derivative of this, the mass lowering operator acting on this, it gives you exactly E2 bar hat times tau 2 square. So the final answer is that you replace this, and that will answer your question. You get something like tau 2 square, E2 hat tau, E2 hat tau bar, and its complex conjugate, which is the same, and it has the right transformation properties. And now it is modular invariant.
And it's now we are integrating over the keyboard.
And now you are integrating over the keyhole ring. Yeah, now you are only integrating over the keyhole. No, because you originally had a E2 tau. This other sum, after all these manipulations and magic, sort of Kronecker limit formula magic, ends up giving you the same function, E2 hat. So originally, you had something like E2 hat times F tau.
Originally, E2 hat was there, and then the other one.
So you actually get quite a beautiful formula, which seems to have counting interpretation because it has a Q expansion. It looks like almost there is a counting interpretation. No, because of the E2 hat. So there are some 1 upon tau 2 pieces, but that we are used to. That usually there can be some divergences coming from. No, meaning E2 has a nice Q expansion, but E2 hat has this 1 upon tau 2 piece. So apart from that 1 upon tau 2 piece, which we know, we also in string theory we get 1 upon tau 2s all over the place, coming from the zero modes. Huh? So there was one constant piece that we had to throw away, and which we are trying to understand for ADS3.
That's not that has no chance of cancelling this tau 2.
No, you can actually play the same game with that term, and what you end up getting is just where did I write the Kronecker limit formula? Yeah, you end up getting just E2 hat, E2, the Eisenstein series without the thing acting on it, without the differential operator acting on it. So you basically end up getting this divergent term. And we don't know how to interpret this divergent term. Yeah, I mean, but I think it's also because we are doing at that loop, or I mean, there is a subleading piece. There is a subleading piece which is of the same order coming from the expansion of the de Sitter. Yeah, because the de Sitter, even when you take L to be very large, it is not conformally invariant and there is a piece left over. So we are expecting or hoping that in ADS 3 cross S3, we can do bosonic string theory in ADS 3 cross S3, and then this piece should not be there. This is something. Huh? No, but in Rindler, we don't have these kinds of nice formulas available. Meaning, we don't have this Harish-Chandra character story developed, but I'm sure it should exist as some kind of a limit of this.
So this is the edge piece that you want to interpret as some edge states.
Yeah, so the edge states have a very nice interpretation. I think they really reflect on the spontaneously broken gauge symmetry. Because, for example, if you take a Maxwell field, it has edge modes. You can ask, why does it have edge modes? Because the Gauss law constraint relates the outside and inside. So in the language of this algebraic quantum field theory, you say that it has a center, meaning the fields inside, right? You have some horizon, and you have fields here. But suppose you have some what is it called, the link variables, like if you think about it, and if you impose some Gauss law constraint, then link variables here and link variables here are not independent of each other because they have to satisfy the Gauss law constraint. So there is no, even if you had a regularized theory like string theory or a lattice regularized theory, the outside and inside don't factorize. So this is to say that the algebraic quantum field theory language, that this is it has a center. It's something that commutes with both the outside and the inside. And that is always present if you have some kind of gauge symmetry. The massive string modes can be thought of using this Pauli-Villar's, sorry, not Pauli-Villar's, Pauli-Fier's method, that you can treat them as with some Stuckelberg fields, you can treat it as an infinite tower of gauge fields. And these edge modes are effectively capturing the physics of this infinite tower of the Pauli-Fier's fields, viewed as some kind of spontaneously broken. So I think it's potentially an interesting quantity in string theory, independently of its connection to entanglement entropy. Now, it contributes, of course, to entanglement entropy. And one thing that you conclude from here is that in string theory, you will get UV finiteness. I mean, this is going back to the question of the UV divergence. In quantum field theory, you had a UV divergence. And how do we get rid of that UV divergence? And as we saw, all the UV divergence comes from this point. And one method for dealing with this UV divergence was this idea of using a replica method, which is what I have been working on for a while now. There also you can show that string theory actually gives answers which are both UV and IR finite, but it was difficult to get a modular invariant answer. So we did not succeed. Witten obtained a modular invariant, sort of not modular invariant, but was able to do this continuation for open strings near a Rindler horizon. But for closed strings, to get a modular invariant expression turns out to be quite a difficult problem. Although you can show that it is infrared and UV finite. So that part we were able to do with Upamanyu. But here the advantage is that even though you are not dealing with the entire entanglement entropy, because some of it comes from the bulk term, the edge modes themselves are UV divergent in field theory. But in string theory, it appears that you may be able to get a UV finite answer. And it would be very interesting if you can calculate it using.
The one thing that confuses me is that even in this, you have this lambda of tau, which means there are 24 oscillators.
Yes, so, but it's a 24 oscillators in some ways restricted to, because you can have oscillators which are oscillating in the transverse direction.
Yeah, but you have those 24 oscillators, but then
On top of that you have. Yeah.
Seems almost like you have more in the edge points than.
Well, that's not clear. If you take a Q expansion, I don't know how you'll interpret this.
These may cancel, right? Are these positive?
No, these coefficients are all positive. Yeah, I don't think they will. But the Q expansion.
Yeah, because it's the Eisenstein sum over divisors, right? Like
So you're saying that it.
Euclidean or something like that.
Yeah, it is correct. What you're saying, it's n.
Divides A.
Yeah. It's n q to the n. 1 minus q to the n. It's 1 minus 24. Yeah, so you can Q expand this for sure. Yeah, there is 1 minus because of the eta function has Q to the, basically you're taking eta to the 24, which has Q product 1 minus Q to the n. No, sorry, how does it work? Yeah. To the power 24. And then you take a log, you'll get log of Q and then log of this. And you take a derivative, then you get these terms. 24.
Why that overall minus sign? That's how it will enter.
You think it should be plus? No, it's 1 minus. Yeah, then you have to take 1 upon 2 pi d by d tau. So we have to take the logarithm of this. So you have to take log Q.
No, that's correct, but I'm just confused about its physical interpretation. Then are you saying that?
You're saying that it's not positive. They are all negative.
The same sign, but.
They're all negative. Yeah, I have no idea. No, it's 1 minus that. It's not entirely clear. You have to expand the whole thing and you have to do the.
This is reducing the number of things.
Maybe just reducing.
Meaning what? Yeah, to interpret this.
Then there are ones which will.
Yeah, I think it's interesting to maybe expand this to a few order and see, but you have to do the tau1 integral to impose, because some terms will not contribute, right? It's not a holomorphic expansion. So
you go to large tau.
or something. You do the expansion. Yeah, exactly.
Then one time
And ask for the first few terms. And whether they have all positive coefficients or not, and whether they reduce compared to that's certainly a good question to ask.
Because you have this times its complex.
Yeah, times is complex. Q and Q bar, they will always come in pairs.
it's again more dangerous because you are getting more than one more than
Yeah, that should not happen. I think the interpretation of these people is that if you look at it from the field theory point of view, for a spin field S, I think there are S square, it looks like they have S square degrees of freedom stuck at the horizon. Like if you have a spin S field in the bulk, it corresponds to S square degrees of freedom. So I think it could be more because of that S square.
Yeah, the reduction is basically in the momentum.
Ah.
Otherwise, in the oscillator, there is no reduction.
Oscillator, there is no reduction, and each field may end up being S square degrees of freedom. But enhancement, but it's it depends on how you count it. It's a lower dimensional enhancement. Yeah.
But it has all the 24 oscillating. That's only you're getting rid of just the longitudinal direction.
But the point is that, which is kind of consistent with the spacetime interpretation, that for every given field, you actually get, for one single field of spin S, you actually get S square degrees of freedom stuck on the horizon with lower spin. So therefore, it can look like the number of degrees of freedom has gone up. Yeah, so there it's some parts of it are actually quite easy to understand. Like you can take a photon, for example. Yeah, if you take a Proca field, like a massive, if you take a spontaneously broken massive vector boson in 3 dimensions, right? So you suppose you have a term like f square plus a mass term. But a good way to do it is using the Stuckelberg field. So you don't, because this is not gauge invariant. So you introduce a gauge invariance by introducing a field, let's say B field, and write it as del mu B minus A mu whole square. So you write the action like that. So you take this action. So it's like more like an axion field. And this has a gauge invariance B going to B plus epsilon, A mu goes to A mu plus del mu epsilon. So you have a gauge invariance. And now you can just go ahead and quantize this field. Some of the edge modes you can actually see, like if you do the Padya-Popov quantization, but not all of them, okay? I mean, maybe, but I'm sure there is an interpretation like that. Okay, I won't be able to. In some, yeah, part of it. So actually you get there are C, but when you introduce the ghosts zero modes don't exactly cancel the, because the ghosts, I mean, another way to say that it is that, yeah, so you will introduce some ghosts CC bar, and the gauge fixing condition is that just, I may be able to reproduce it, but basically, the main point is that the ghost fields don't have a derivative, whereas the B field has a derivative. So the zero mode of the B field doesn't actually cancel. Normally, when the determinants cancel of bosons and fermions, but the zero mode of the B field doesn't exactly cancel. But that's only part of the contribution to the edge modes, and there is additional contribution. But the point is that this is a gauge invariant action, and you can just quantize it, and this is what you get. And I think I'm not able to do justice to their paper, but I mean, I think because I'm not able to recall all the arguments, but I think they have spent a whole chapter explaining how to get all this in that 100-page paper. Yeah, so it's okay. Thank you.
Any other questions, yeah, Rishabh?
Worldsheet calculation for this?
At the moment, yes, not. Yeah.
Like the prediction for what worldsheet
Would give, yeah.
So I mean, in worldsheet also there are two ways of, like, one is like partial figure, like Minkowski-Rindler did for ATS, but the other is like can calculate a trace in the scene.
If there's a dual safety.
Not in the dual, like for free boson I can actually calculate it. Right? There is a partial figure way of doing, and there is a trace.
You're saying that in the worldsheet trace, a worldsheet trace
if there's a
should be somehow connected to this Q expansion. The worldsheet trace, exactly right. That's what I was saying when I said that it has a state counting interpretation, that it looks like it's a worldsheet trace over some Hilbert space which we don't know.
Is it like precise, like close to like the Hilbert space will look like this?
Yeah, we don't know. I mean, another thing is that this, I would like to connect it also to from the other direction. I mean, we had this replica method. So in the replica method, should also give this as an answer, if you can do the analytic continuation. So it's also hopefully connected to that. No, by L going to infinity limit, what you mean is simply that wherever you have, it's like in, suppose you had the sum over n plus 1 whole square, right? And you had to sum over n. So you divide by L square, and then you call P is equal to, actually, this goes from -1, so just make it n square, okay? Let's call it m square. M goes from 0 to infinity. Now you can call momentum to be m over L, like we normally do, right? When we go from a circle to a, and delta P is like 1 upon L. So you can write this as delta P, P square, L cube, and turn this into an integral, right? And so that's what I meant by large L limit. In the large L limit, if you had discrete momenta, they kind of come close to each other and become a continuous momentum. That's all I mean. And there will be corrections upon 1 upon L square, which can be important for addressing this subleading term, which we are not getting right. So graviton is massive. I mean, so the only massless mode where your complementary series is relevant is the vector boson, photon. Everything else is massive. I mean, all the massless modes like graviton are not propagating. That's another. The only propagating massless mode is the spin 1. Everything else is, huh? In 3 dimensions, that's the property, right? In 3 dimensions, graviton doesn't propagate.
So this is free theory, right?
This is free theory.
No, this is free. Interaction.
G Newton doesn't appear in this. Okay.
Manifold target space, like very simple, like
No, but he's saying the Euclidean de Sitter, if you treat it as an SU2 Weismann-Witten model, S3 times something else, you'll probably need some, I mean, no, you can just take no, okay, just as a conformally invariant theory, you could treat it as an SU2 level. Because it will have some central charge and but it will have a B field. So it won't be what you want, maybe. It will have a B field, H flux.
Should be, I would imagine, yes. I mean, at least in the large,
Yeah, H flux, yeah. Yeah. That answer you can write down. And then, of course, the central charge you'll have to adjust with the instead of yeah, you can. Yeah. Mm. But there also you have flux.
There also you have flux. There's a flux is spread over the entire.
Yeah. Yeah, but that applies to what Rishabh is also saying. So you can SU2 level K, but take K very large. Then it has central charge 3.
Somehow that should pop out this E2s. Yeah, that could be an interesting. That's what we are expecting to see also from the ADS3. We are looking at ADS3 process, which is actually a reverse of this, right? I mean, you're doing ADS3 plus S3, but you put that as S3 plus 2. It's the same thing. It's the same calculation. But this thing, the
Yeah, ADS3. But you may not need the ADS3. I mean, ADS3 brings its own boundaries and everything like that. So, I mean, maybe what, like the central charge for the SU2, this thing is 3K over K plus 2.
Yeah. So
Then you
just put
add
a-
something which makes it 3.
Yeah.
And then you take K very large, and then the other piece will become essentially 0.
So we are looking at it as the ADS3 plus S3 because those things are also known.
Right, that's the Maldacena-Uguri this thing, yeah. So in fact, yeah. So just as this thing, the reason we wrote this old paper on this ADS3 was we were trying to do something in the similar philosophy that, you know, the spectrum, we wanted to reconstruct the world sheet theory at that time. So that's the reason why we did this whole calculation at that time for the same philosophy to try to reconstruct follow the Polchinski logic and this thing. But we did, well, no, but now, okay, through other ways we managed it, but that's the tensionless limit. But I was, this thing that there, you know, the symmetric orbifold, you know, the spectrum. So then I was hoping to reconstruct the world sheet theory for the symmetric orbifold because you know the spectrum, you follow. No, ADS3 times S3 will be, so the symmetric orbifold knows about the whole spectrum.
Not only S3, but also ADS3.
But we did S3 and ADS3. We did,
because it's simple
and then you kind of continued to ADS3. And S3, we didn't do that in that paper, but that was the idea that you
that string fields moving in that
background, yeah. And so in that sense, it was, yeah. Okay, thank you again, and to Atish, and hopefully come again and give more talks on this. So we should also get Upmanyu to come and spend some time. Yeah, he'll probably have more time than you. So.
Or also Eleanor, maybe you can.
Eleanor, she's a graduate student.
She's a